Yes. Hello, viewers. Welcome to my channel. In the present class, we are going to discuss the topic the ratio of specific heat of gases. So we have to derive the expression Cp by Cv equal to Es by Et that equal to gamma. So in this expression, Cp stands for specific heat at constant pressure, Cv specific heat at constant volume, Es elasticity modulus in adiabatic process. Et elasticity modulus in isothermal process. So it is a ratio of elasticity modulus in adiabatic to isothermal process. So that should be gamma. Because Cp by Cv equal to gamma, we know that. Here we will prove that by using the Maxwell thermodynamic relations. Cp by Cv equal to Es by Et that equal to gamma. Right. So before going to the derivation, let us derive what is Cp and what is Cv. Specific heat at constant pressure is nothing but the amount of heat required to rise the temperature of 1 mole of gas through 1 degree centigrade is called as molar specific heat at constant pressure. That means what? At constant pressure, if you take 1 mole of gas, so whatever the amount of heat needed to rise its temperature by 1 degree centigrade, that amount of heat energy is called specific heat at constant pressure or molar specific heat. Okay, heat capacity at specific constant pressure. The second one, molar specific heat at constant volume, Cv. So here we are keeping the volume constant, right? At constant volume, the amount of heat required to rise the temperature of 1 mole of gas to 1 degree centigrade is called as molar specific heat at constant volume. It is denoted with the Cv. Okay, so molar specific heat at constant pressure Cp, molar specific heat at constant volume Cv. So our intention is we have to prove this one. Cp by Cv equal to Es by Et that equal to gamma. Right, sir. This is the approach we are following here. Right. So let us go for derivation. The bulk modulus of elasticity the coefficient of volume elasticity. It is given by E is equal to capital E equal to volume stress by volume strain. You have some idea about elasticity of solids, liquids, and gases. All of you know that solids have the three types of elasticity modulus. One is Young's modulus, the second one bulk modulus, the third one rigidity modulus. Okay, Young's modulus, bulk modulus, the third one rigidity modulus, Y, K, eta. But in the case of liquids, only bulk modulus exists. Okay, volume elasticity modulus is also called as volume elasticity modulus. Only that exists. When we talking about the gases has two types of volume elasticities. Why? Because the temperature of the gas can be changed in the two different ways. If that the gaseous system subjected to the adiabatic process, then volume elasticity at constant entropy. Because in adiabatic process, entropy of the system is constant. So that's why the corresponding volume elasticity is termed as volume elasticity at constant entropy. If you consider the isothermal process, in isothermal process, also you can change the volume. You can change the volume by keeping the pressure constant, or by keeping the volume constant, you can change the pressure. The pressure is constant. With increase of temperature, the volume changes. If the volume is constant, with increase of temperature, the pressure changes. So that's why in isothermal process, so there the volume elasticity is termed as isothermal elasticity. Okay, in adiabatic process, the elasticity is called as adiabatic elasticity. Adiabatic elasticity is denoted with ES. Adiabatic elasticity is denoted with ES, E subscript S, where S stands for entropy. Since adiabatic process entropy constant, we are denoting with this letter. In isothermal process, okay, in isothermal process, the elasticity modulus or volume elasticity is denoted as Et or E theta, E theta, because their temperature constant, T, capital T constant or theta is constant, right, sir? Now, in general, uh, the volume elasticity is defined as E is equal to, capital E equal to volume stress by volume strain. Right, sir. Young's modulus, how we define Langmuir stress by Langmuir strain. Right, sir. Volume elasticity equal volume stress by volume strain. This is a bulk modulus or bulk modulus elasticity coefficient. Rigidity modulus equals sharing stress by sharing strain. Right, sir. So here we are taking the volume elasticity, right? So it is defined as volume stress by volume strain, that equal to minus dP, change in pressure dP by volume strain, that is delta V by delta V or dV by, right, sir? So by that equation becomes as minus V dP by, okay. So this is a general representation of volume elasticity, general representation of volume elasticity, right, sir? Now, during isothermal process, since temperature is constant, isothermal elasticity is given by E subscript capital T equal to minus V dP by dt or dou P by dou T over T. Right, sir? According to this expression, we are writing general expression. What we have written, capital E equal to minus V dP by D. Now, when you talk about isothermal process, isothermal elasticity, we are writing E subscript T equal minus V dou P by dou T over T, equation 1. But during adiabatic process, because their entropy is constant, the adiabatic elasticity is given by E subscript S. E subscript S, that equal to minus V dou P by dou V over S. So whatever we are writing over the bracket, under the bracket, that physical constant, that physical quantity is constant in that process. Right, sir? Now, so ET and ES we have written. Now, by dividing these two equations, ES by ET equal to minus V dou P by dou V over S is by minus V dou P by dou V over T. Right. So minus V cancel. So that gives dou P by dou V over S by dou P by dou V over T. Okay. So this is way. This equation just we are rearranging. In the numerator, we are rearranging dou P by dou T into dou T by dou V over S by the denominator term also rearranged. So that is written as dou P by dou S by dou V over T. Got my point? So now, by separating the terms, dou P by dou T over S and dou T by dou V over S by, in the denominator, dou P by dou S over T and dou S by dou V over T. This is equation 3. Okay. Now we are using the Maxwell thermodynamic relations. So that's why already I told you that Maxwell thermodynamic relations you should remember. So without knowing that, you cannot derive this expression. So therefore, you should thoroughly about these 4 Maxwell's relations. Right, sir? So in the numerator, in the equation 3, what is the first term? Dou P by dou T over S. We can write it as 1 by dou T by dou P over S. But according to the Maxwell's second thermodynamic relation, dou T by dou P S is equal to dou V by dou S over P. So therefore, dou T by dou P over S, I am writing 1 by dou V by dou S over P. Again, by rearranging that, dou S comes to the numerator, dou S by dou V over P. Right, sir? Similarly, in the numerator here we have the term dou T by dou V over S. So that equal to, from Maxwell first equation, dou T by dou V over S is equal minus dou P by dou S over V. Okay, next. Coming to the denominator of the equation 3, the first term, what is that? Dou P by dou S over T. Dou P by dou S over T can be written as 1 by dou S by dou P over T, that equal 1 by, according to the Maxwell fourth relation, dou S by dou P over T equal minus dou V by dou T over P, that equal minus dou T by dou V over T. Okay, so now next term, dou S by dou V over T is equal to, from Maxwell third relation, dou P by dou T over T. So now let us substitute these values. Instead of dou P by dou T over S, we will substitute dou S by dou V over P. Instead of dou T by dou V over S, that is what, minus dou P by dou S over V. Instead of dou S by dou P over T, let us substitute minus dou T by dou V. Similarly, dou S by dou V over T equal to. By substituting the above values, whatever we got, then the equation 3 changes as ES by ET equal to dou S by dou V over P minus 1 into this and minus into this, minus 1 cancel, right? So, then dou S by dou V over P here, in the denominator dou T by dou V over P. Dou V cancel, we'll get dou S by dou TP. Okay, next, dou P by dou S over V. Here denominator dou P by dou T over V. Dou P cancel, dou T by dou V over dou S by dou T over V. Right, sir. Now, so that equals to, by multiplying with the T in the numerator and denominator. So what we get, T dou S by dou T over P by T into dou S by dou T over P. See what I'm saying? So this equation on right hand side, just we are multiplying with capital T in the numerator and denominator. So then we are getting T dou S by dou T by T dou S by dou T P7. But T into dou S is dou Q according to the second law of thermodynamics. Hence, this equation becomes dou Q by dou T over P by, in the denominator, T into dou S, we are writing dou Q by dou T over P. Right, sir? But dou Q by dou T over P is nothing but what? This is specific heat at constant pressure, molar specific heat at constant pressure. Dou Q by dou T over V represents what? Molar specific heat at constant volume, equal to Cp by Cv. Right, sir? Actually, we know that ES by ET, the ratio of adiabatic elasticity. Adiabatic elasticity ES is equal to minus gamma dp by delta V by V or dV by V. Okay, and isothermal elasticity ET is equal to minus dP by, that is volume stress dP by change in volume delta V by V, volume strain delta V by V. Okay, so ES by ET, by taking the ratio ES by ET, then what you get? Gamma. So here we prove that ES by ET equals Cp by C, but ES by ET equal to gamma. Therefore, ES by ET is equal Cp by Cv, that equal to gamma. So finally, we prove that the ratio of molar specific heat at constant pressure to molar specific heat at constant volume is equal to the ratio of adiabatic elasticity to isothermal elasticity, that equal to gamma. Right, sir? So this is about the ratio of molar specific heats derivation.